Okay, so in the next set of mBed microcontroller tutorial videos, we're going to be covering a few things called like analog to digital conversion and digital to analog conversion. So with that in mind comes the idea of exactly what is digital and what is analog. So in the case with, for example, the analog to digital converter, it converts an analog signal to a digital signal, and for digital to analog conversion, it converts a digital signal to an analog signal. So we're going to go ahead and discuss exactly those two types of signals and how they behave. So the first one is digital, which we're going to be using red to use as an example as the color of interest, and analog is going to be denoted as a blue. We'll just move it a little bit more over to the right side so we have a little more space to discuss it. So analog right here. Okay, so we're going to go ahead and discuss digital. So the idea behind digital is the signal has a fixed output. So either 0 or 1, which is typically binary, so 0 or 1, which is binary. Or it could also be something like a limitation between a set amount of values where it could be something like 0 to 255, and integers only. So you only have 256 values. So with that in mind, also comes the idea of exactly how computers interpret signals. So they interpret things digitally as you would expect. So with that in mind is also the idea of exactly how to read binary numbers. So a computer won't read in 255, but instead read a series of zeros and ones that interpret itself to become 255 or something like that. And so we're going to go ahead and explain exactly how a computer interprets binary. But with that, we would also need to keep in mind of that a computer interpreting binary is fairly similar to exactly how we interpret numbers ourselves. So let me just go ahead and just throw out a number, say like 5,000. So notice that the number, each of these numbers is in a placeholder. So there's ones, tens, hundreds, thousands. And so the way that you actually recognize these, because typically our numbers range from 0 to 9, and we put them in a specific placeholder to interpret its actual value by magnitude of 10. So in this case, this is actually 0 times 10 to the 0th power. This is 0 times 10 to the first. This is 0 times 10 to the second. And this is 5 times 10 to the third. And the idea is that when you sum all these values together, you effectively get 5,000. Oops, that looks like a 8, but that's 5,000. So the idea behind this with binary is that it does base itself on this placeholder, based on this placeholder sort of system. But instead of using base 10, you use base 2. And instead of a number from 0 to 9, you use only 1 or 0. So we're going to go ahead and just write a binary number just to give you an idea of all that. But before that, we're going to go ahead and erase this so we have some space to interpret. So I'm going to just say something like, we're going to say 0, 1, 1, 0, and a 0 over here, and 1, 1, 0. Okay, so this over here is 2 to the 0th power times 0. This is 1 times 2 to the second, to the first, my bad. This is a 1 times 2 to this 2 to the second. Got a little bit ahead of myself here. This is 0 times 2 to the third. And then this is kind of the exact same arrangement, but again with the magnitude as well. But you can see that everything is summed like this. So we can pretty much interpret this number. We're going to ignore these zeros because the zeros don't actually add up to anything. But we can see over here that it is the way that we sum it up. It's going to be 2 to the 6th plus 2 to the 5th plus this one is 2 to the 0, 1, 2, 2 to the second. This one is 2 to the first. And if you add these numbers together, it's 64 plus 32 plus 4 plus 2, which equals to 32, 6, 96. 96 plus that is 100. So it's 102. The number is 102. So 0, 1, 1, 0, 0, 1, 1, 0. is 102. So that's exactly how a computer interprets binary. And this is fairly important to understand a few things to keep in mind. So the integer value or the magnitude depends on its bit depth. So in this case, this is an 8-bit number. An 8-bit at maximum can be only up to 255. So 255 is the maximum value for 8-bit. And the way that you can tell this is you simply say the maximum value is 2 to the 8th. Or actually, the number from 0 to 255, and which in fact means that there's only 256 values. So an 8-bit value is limited to a number from 0 to 255, which means it only has 256 numbers in between its range. And if you go up to 9 bits, that pretty much means you effectively have doubled this. So this is 2 to the 9th. And that means that your range of values are going to be from 0 to 511, which means you have 512 set values to play with. And if you go to 10, 2 to the 10th, you have effectively 1024. If you just multiply each of these by another factor of 2, you get up to the next set of range of values. So in our case, we did talk about microcontrollers being 32-bit. They're being 32-bit. So the idea is that they can manipulate at most at any time 32 bits. So 32 bits is actually quite a magnificent number. And with the whole things with 8-bit microcontrollers, they can only manipulate 8 bits at a time. So you can definitely tell the range of exactly how much data you can manipulate at any single point in time when you're running an operation. So that also comes with the idea of this thing called bits. So I'm going to go ahead and erase this over here, and we're going to go ahead and discuss something called analog. So analog is actually a lot easier to explain than digital, and probably we should have discussed analog first, because analog is pretty much how the world behaves. Digital was kind of like this artificial creation to make it so that we could make computers do things for us. So analog is continuous and like infinite range of values, or near infinite. So an analog could be, something from 0 to 5 volts, and it could be any voltage in between 0 and 5 volts. You can be like 1 volt, 2 volts, 3 volts, 1.5, 1.54, 1.59, 1.599999 volts. So this is pretty much how like basic, passive circuits work, op amps, that sort of stuff. So analog itself is important because what it pretty much is how the world behaves, and so there's going to be a need to convert these signals in between. So the microcontroller can interpret signals in the analog domain, and while at the same time also outputting an analog signal to manipulate perhaps an analog circuit. So what we do have is this thing called an ADC. So an analog to digital converter pretty much converts an analog signal to a digital signal, and then on the other way of doing it, a digital to analog converter converts a digital signal to an analog signal. Okay, so with ADC and DAC in mind, we're going to go ahead and explain exactly how to actually convert these two signals. With that, we're going to go ahead and start with the example. We're going to go ahead and just create some arbitrary analog signal, say a sinusoid that goes like this. Okay. So the idea behind analog to digital conversion is that the microcontroller is going to only pick up a few sample points here and there in between this signal. So it's going to it's going to read this one, and then it's going to read the next one, and then it's going to read the next one, and there's going to be this constant like little gap in between. So it's not going to pick up all the data, not this continuous range of values, but only just a few set points here and there at some specified rate. So this rate is called the sampling rate. And the idea is, the better the sampling rate, the more efficient you can actually get all of these little signals. And another thing you need to keep in mind is that if this is a constantly moving signal of a certain frequency, your sampling rate has to be greater than this frequency by at least 2 times, in order to pick up this signal, because what's going to happen, say for example, my sampling rate is half of this frequency, I'm only going to pick this one up right here, and then I'm only going to pick up this one right here, and I'm going to lose this entire like little chunk right here of data. So things to keep in mind. Another thing to keep in mind though is that the way that the microcontroller works is that it's based, the maximum voltage signal is based off a logic standard that it has. The microcontroller for the ARM series is a 3.3 volts maximum. So if, say, your voltage signal goes beyond 3.3 volts or below 0 volts, because the range is from 0 volts to 3.3 volts, so this shoots all the way up over here, and then it goes and dips down like this. What's going to happen is that the analog to digital converter is going to, at max, peak out at 3.3 volts. So it's going to just read something up right here at maximum, and it's going to lose the rest of the data that goes up here. So if this is 6 volts, the analog digital converter is going to register it as 3.3 volts. And say over here, it's only going to register this entire chunk right here as 0 volts. So you can't read negative. It can't read negative voltages. So the small limitation with analog digital conversion. On top of that, there's also the other conversion, which is the bit depth between these two ranges. So the idea is that it won't be able to pick up, 1.0000001 volt. It'll maybe register that as like 1 volt instead. And the idea behind that is that there's a set number of tick marks in here that the analog to digital converter can become. So say for instance, this is one tick mark, another tick mark, and like there's these set small values that it can only become. So it can only become this, it can only become this. It can't be anything in between these two little tick marks. And that's called the bit depth of the ADC. Bit depth. And in our case, it's 16-bit. So we have a 16-bit ADC. So what that pretty much means is that it has 2 to the 16th different values between 0 and 3.3 volts. So the absolute smallest voltage that the analog to digital converter can pick up is something that is 3.3 divided by 2 to the 16th, which is roughly around like 50 microvolts. So it's actually fairly good as an analog to digital converter. 50 microvolts is, this is something that you can actually pick up like an EKG signal with. And another instance, the cell membrane is typically 60 millivolts, so you can actually pick that up. So this is just a few things to keep in mind, and that's also partly another reason why we picked the KL25Z, because of the 16-bit ADC, which is useful for a lot of biomedical applications. And with that too is also the idea of the digital to analog converter. So it works a lot like this, but it goes in the reverse direction, where it's going to convert some sort of digital signal to an analog signal. So it's going to trying to make this little, this blue wave right here. So I'm going to go ahead and just start over here. Actually, we might want to erase this, and we can go ahead and restart over. So the idea behind this, again, there's going to be some sort of like, the inverse of a sampling rate. So this is going to be the time it takes for the microcontroller to change voltages constantly over a set period of time. So this is, we're going to go ahead and just draw a red graph to indicate that this is the digital signal. And then we're going to draw a hypothetical blue signal that the digital to analog converter is going to try to become. So something that looks like this. And again, the issue is that it's going to be ranged at most from 0 to 3.3 volts, because that's the microcontroller's logic levels. So you can only go from between that range. So 3.3 volts is the maximum. And this is 0 volts right here at the bottom. So what it's going to do is that it's going to, create some arbitrary voltage, and then there's going to be some sort of time lag between the time it takes to convert to the next voltage. And once it gets to the next voltage, it's going to go ahead and convert that to the next voltage, and it's going to go ahead and convert to the next one. And it's going to effectively what it's effectively going to become. It's going to be a series of little jagged little rectangles. So the time between this is like the time it takes to convert the voltages in this signal, and so it's effectively going to look a lot more like this. And the way that you can make this a lot better is to speed up the time it takes to convert the voltages And again, with the idea of bit depth, it can only be a set amount. It can only be set voltages. So in the case with the microcontroller, we have a 12-bit ADC or a DAC, sorry. So this means that I can be a range of 3.3 volts, output something from something within this range. So this is each of these little steps that it can become. So that's effectively how the digital to analog converter works, pretty much kind of in the same way. And then you could do a few other techniques to make this a lot more smooth, but we're not going to be focusing on that. Instead, we're just going to be focusing on exactly how to use the microcontroller to output this sort of signal. So with that, we also need to look at the pinouts of the KL25Z. So right over here is actually the listing, and over here you can actually see that this is the analog inputs. So you can actually use PTB0, B1, B2, B3, C2, and C1 are all are 16-bit ADCs. So you can use any of these. And there's only one digital to analog converter on this board, which is the PTE30, which was the 12-bit DAC. And that's pretty much it. And we're going to go ahead and write up some code to use the analog input and the analog out.